Hey, you!
Yeah?
Let's fight!
Okay. Sorry.
What is autonomous? Autonomous is the 30-second period at the start of a match where the robot drives itself.
But by team standards, autonomous is also the long, tedious process that team coders have to put themselves through every single season. It takes a lot of trial and error just to have an autonomous that only works 60 to 70% of the time by your first tournament. Honestly, there has to be a better way to program your autonomous.
Why, Jackson, what if I told you that you could program your autonomous in less than 10 minutes within an inch of accuracy?
There's no way, okay, there's no way that's possible.
It's true. Hi, I'm Eric,
And I'm Jackson.
and welcome to Chat.
CHAD is an acronym for Chassis Owned Autonomous Designer.
Basically, it's an online interface hosted at ftcchad.com that's completely free for everyone to use.
All you simply have to do is select your ideal chassis type, and then fill in some general robot information, and then you are good to start drawing out your ideal autonomous. After you're done drawing out your ideal autonomous, hit the generate button, and CHAD will instantly generate your code for you in a matter of seconds, assuming you have a good Wi-Fi connection.
Chad works with 4 different types of chassis. The traction chassis with 4 traction wheels and motors on all of them. The omni-wheel chassis with 2 traction wheels and 2 omni wheels and 2 motors on the traction wheels. The mechanism chassis with 4 mechanism wheels and motors on all of them. And the holonomic chassis with 4 omni wheels set at 45-degree angles and motors on all of them as well.
Something that we want to preface before we get a little bit more into the presentation is that CHAD is not meant to do it all. It is meant to be an unfinished product so then other teams that are using our product can go in and add their own code so they still get the learning benefit out of this.
However, you can add sensors and extraneous functions to add a little bit more to your autonomous so it's more complete and can do more advanced things. In order to use CHAD, you're going to have meet a few requirements on your robot. First of all, you need to have a rev hub, as in expansion or control. You need to have one of the 4 compatible chassis, and you need to have encoders on all of your motors.
Assuming you have the previous listed parts, you're ready to finally start programming your autonomous using CHAD. The first step is to select your chassis. For this demonstration, we use the partial omni-wheel drive because that's what we used in our Rover Ruckus season, which is shown up here when we took the video.
Now, for the boring part. First of all, we're going to enter some information like the autonomous name, the gear ratio on the encoders, and the dimensions of the robot. There's also some custom inputs that you can add.
Now you're ready for the fun part. You get to draw out your autonomous. First, you need to select your starting side. For the Rover Ruckus season, you could start in one of 4 locations, being here, 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 and here. But for the Ultimate Goal season, we have updated the FTC CHAD website for the starting tapes on the bottom, so your robot will always be in contact with the wall when starting, as specified in Game Manual 2.
Now that you've got a starting point, you can actually start doing some steps. So, choose the step type you want, and move your cursor around the field in order to specify where you want the robot to end up. When you're done, click to confirm the position.
If you like the move that you just made, you can go ahead and click the done button, and the step will show up over here. If you do not like that, you can always hit the garbage button and it will delete the step. The red X you saw as well is to delete all of the steps that you already have in there, which you can do if you truly do hate yourself. So,
once you've built an autonomous that you're happy with, you can go ahead, click the generate button, and copy the code right into Android Studio, and it will work just like that. Then, copy the calibration code from a little bit further down on the website, put that into Android Studio as well, and you're ready to start calibrating. This is an important part of the process where your robot is going to move 20 inches exactly in order to help you basically see how well your chassis is going to move. If your chassis doesn't move exactly 20 inches, there's a few things you can do. First of all, you can change the calibration bias. If that still doesn't work, you're going to need to troubleshoot it with the tips and info page on the website. And if all else fails, reference our full calibration guide that we have on YouTube, the Thunder Penguins channel.
Again, we do want to highlight the fact that Chad will only do the chassis movement during autonomous. It'll still be dependent upon the teams to program their mechanical subsystems, like for example this year, launching the rings into the high goal during autonomous. So that still leaves some problem-solving aspects for team coders to problem solve and go through, so they still learn something out of the season.
Now, Eric, you may be wondering, how did you come up with this fantabulous idea?
But Eric, how did you come up with this fantabulous idea?
Well, Jackson, it all started last year at State, when we were watching as teams were doing autonomous up to the very last second. Actually it was the year before at State, but we were watching as they were doing things at the very last second, doing trial and error, changing things one step at a time.
Okay, I thought you were going to go through it. I think this is just another practice run, so there's still tiny little parts that I can work on and you can work on, but we'll do one more run after this and we'll call it good.
Okay.
So do you want to do all of this, or do you want me to step in and do the time-consuming trial and error process?
Oh, right, I was supposed to do this, wasn't I?
Yeah, okay. How about you just go to, we saw a lot of teams having troubles with their autonomous at State in 2018.
Mm-hmm.
That way you don't have to worry about saying the wrong year, so just say in 2018. And we started questioning why teams were programming their autonomous at such a high level of competition up until the last minute.
Right. And we came to the conclusion that it's because
I'll say that part, yeah.
Okay.
Do we want to restart, or do we want to finish the rest of this?
Let's just keep powering through.
Okay.
So we're like, we need to find a way to improve the code experience. Now, in the past, a lot of teams have built what's called a code base, where they put all the code they've got into one spot, like GitHub, and then other teams can download it and use their code. The problem with this is it's a somewhat complicated process, and you've got to figure out what each function does and how to apply it. So we were wondering if there's a better way to build personalized code and just have it ready to go from the start. And that's where the idea of a website came from. But the one problem was we didn't have any experience with web development at all.
I can help you with that. I know all about websites.
Yeah. Thanks, Christine. So once we've got our mentor, we can actually start doing stuff. But we need some chassis to test with.
So, evidently, the building portion of FTC Chat was significantly harder than the programming, I hope you understand. The first thing that we need to do is decide the 4 chassis types that we wanted to use. So, we were thinking about our previous years at FTC, and we decided to use the 4 traction wheel chassis and the partial omni wheel chassis, because we tend to see the rookie teams using those a lot more in comparison to the other 2 chassis we chose, the holonomic and the mechanom, which are highly chosen by veteran teams because of their strafing ability. We also need to design and build these chassis, of course, and we realized quickly that we didn't have enough electronics like rev hubs and batteries to mount it to every single chassis that we had, so we had to come up with a quick way to be able to mount our rev hub from one chassis to the next.
Welcome to the live demonstration. Jackson is gone, he's vaporized, so let's begin. As you can see here, we're going to be using a holonomic chassis. So that's what we'll choose on the website. So if you look up here on the website, we choose holonomic, very simple. Let's name it Hello World because of coding. We'll leave this default bias there for now. I believe, let's check the gear ratio of these motors. So these are 20 gear ratio, you can tell by, it says it on the motors. So pretty simple, we're just going to enter the preset 20. So the field this year is you can choose to be on any one of these tapes and face any direction, but you've got to be touching the wall as well. So let's say we choose right blue, we can face any direction like this, but we've always got to be touching the wall. So let's say we're just facing straight forward for now. And where do we want to be? Doesn't really matter in this case. Let's just face directly forward and choose a distance. So how about we go 40 inches for now, just a really simple autonomous to kind of show what it can do. We'll go 40 inches forward. Next we do this. Now you can do this by moving your cursor around, or if you want to be more precise, you can use this angle thing here to get very precise numbers. So let's go a nice 90-degree turn, just like that. And let's do some strafing now too, because we are using a mechanism chassis. We'll strafe exactly 40 inches back. And you can see we can get exact numbers just like this. So 40 inches, and it's all going at a speed of 0.2, which is like 20% basically. But that'll be good for our purposes right now. Also, these dimensions, in this case, we don't really need to change them because it's not going to really affect the code a whole lot. So let's go ahead and click generate, and boom, there's the code. Fantastic. So, all we need to do to get the code is copy the clipboard, open up Android Studio, create a new class, and make sure when you're naming the class, it's case sensitive, so you've got to name it exactly the same thing as what you put on chat. So we put hello world, we're going to keep it hello world just like that. Now we're going to select all the code and paste it right in there, and boom, there's our new class, all done. Fantastic, you can see it right here. Next, we do want to calibrate it. So there's a chance that our wheels might have some slippage and stuff, so we're going to want to calibrate it. Create a new class. We're going to call it calibrate with a capital C. It is case sensitive. Remember the capital C, calibrate. And there we go. Select all, paste it in there, and it's done. Fantastic. So all that's left to do is we want to upload it to a robot. So let's go ahead, plug it in. You can also do this wirelessly if you want. Doesn't make a difference. We're using a control hub. You can also use a robot controller or phone. Doesn't make a difference. Everything is pretty adaptable when it comes to CHAD. And just make sure that you put the code directly in this org.firstinspires.ftc.teamcode file. It's got to be right in there, or else there might be some issues. If you do want to change the folder, what you've got to do is go up to the top here and just write dot whatever folder you're putting it in. So, but for now, we're just going to put it right in team code. I believe it just uploaded. So we're going to open up our driver controller. Here we go. We'll unplug this. And now we're ready to run the robot. So, let's run our calibrate first. So the calibrate is going to run the robot 20 inches. So we're going to put our robot here, set in a nice spot like this, grab our tape measure, and set it in a spot where you know you can measure easily. So let's put it here for now, right in line with this corner part there. Make sure you're facing exactly forward, initialize, and go. Alright, let's see where we're at. 18. So, this is not 20 inches, but that's what calibration is for. We're going to grab this. Let's go to a calculator. We wanted to go 20 inches, but we only went 18. So, we're going to take our desired divided by how far we went, just like this. Keep in mind, we do already have a bias here, so let's multiply that by our existing bias. Just like this. This will be our new bias. Let's copy that and slap it into Android Studio. And you can see this number is bigger, so it makes sense our robot is going to go farther than before. So, let's go ahead, plug this in. Oh, and make sure, if you get a new bias, to change it with all of your programs, just like that. That's important. So we'll plug it right back into the robot. Just like this. It's connected, there we go. It's gonna run a little bit here. If you're wondering what I'm doing on the screen right now, this is actually the process for connecting to a control hub wirelessly. So you've got to first connect the robot initially. So you're going to want a Wi-Fi dongle like this, which will connect it wirelessly. And then once it's connected, if you get a plug-in like this on Android Studio, you can click this connect button and it will connect automatically, just like that. So it looks like our build is complete. There we go, build successful. So let's unplug this right now. And proof that it's working, you can see still connected to the control hub right up there. So it is going to wirelessly upload if we need to upload it again. But we shouldn't because we've just calibrated. So let's run this again. Just like this, line up our robot, run the calibrate file, and go. And look at that. If you come in close, you can see this is basically exactly 20 inches. Just like that, within an inch of accuracy. So, now that we've got it calibrated, take this back, let's run our autonomous. So we'll just put this wherever for now, or I guess we can lay out our tape measure just to see how accurate it is. We set it going forward 40 inches, just like this. So let's run Hello World on our driver station app, and go. There it goes. Forward, rotate, and strafe back to the position we started in. And if you look, that's exactly going to line up with the position you started in. It's a little tilted, but that's just because of holonomic. So, there you go. And that's a full CHAD. Do you see how quickly that took? Less than 10 minutes. And that's the appeal of CHAD, is you can do things quickly. Obviously, if you want to do sensors and stuff, you're going to have to do that afterwards, but movement, all done.